Hello children, this is once again Rupa Madam. Today I am with an important topic from the chemical bonding that is known as VSEPR theory. Okay, in short, I wrote as VSEPR theory where it is valence shell electron pair repulsion theory. Okay, and this theory is used to explain the exact shape and bond angles of covalent molecules. As we all know that, as we all know that the covalent bond is directional. So to explain the directional properties, to explain the directional properties of covalent bond, first time Linus Pauling explained that atomic orbitals overlap. Atomic orbitals overlap to form covalent bond. Means overlapping of orbitals are involved. Then, according to this overlapping of atomic orbitals, which is explained as VBT, valence bond theory, then all the pure valence orbital must involve. If it is so, any molecule like ammonia, NH3, which are using two, more than its two or three atomic orbitals of valence shell, they must possess about 90 degrees of a bond angle and they must have approximately an L shape. But the water molecule, the water molecule, if you see here, water molecule, everyone knows H2O, water molecule is an angular shape, is an angular shape, and ammonia NH3 formula, it is a pyramidal shape. It is a pyramidal shape. Okay. So according to valence bond theory, these two molecules must have about bond angle of 90 degrees, but not. But if you see here H2S molecule, H2S, this molecule fits exactly in the VBD theory. Here, around the sulfur, two hydrogens are there with covalent bond, and here the pure p orbitals of sulfur atom is involved. So therefore, here SH, this SH bond angle is found to be 90 degrees because of pure p orbitals. Because of pure p orbitals. But in case of this ammonia and water molecule could not work. Okay, so therefore some change must be brought in the atomic orbitals. Then the same Linus Pauling, along with Slater, okay, London different scientists, they developed that here in a covalent bond formation, pure atomic orbitals will not participate. Okay, there is some change is brought into the atomic orbitals, and that is what a hybridization. That is what a hybridization. So, in a molecule, the central atoms valence atomic orbitals which are participating in bonding. Means we all know that the valence electrons, the valence shell, that is last shell electrons of an atom undergoes a bond formation, involved in a bond formation. So according to VBT, it is explained that these valence shell atomic orbitals undergo overlapping. So if it is really pure orbitals, really every molecule should have 90 degrees of a bond angle. But actually what the bond angle of water molecule is 104 degrees 5, 104 degrees 5 minutes. Whereas in ammonia, 107 degrees. Practically, experimentally they are proven. So to explain the exact shape and exact bond angles, some little changes brought in pure atomic orbitals. That concept we know as hybridization. So according to hybridization, what happens? The valence shell atomic orbitals intermix. When they intermix, okay, like s orbital intermix with the p orbital, and we know that s orbital energy will be lesser and p orbital energy is more, and as their azimuthal quantum number values are different. Their shapes also different. Though the s orbital, p orbital may be present in the same outermost shell, okay, same orbit, same energy level, but they differ in little energy. Okay, so this almost same energy orbitals. Sometimes inner orbit or outer orbit also will combine. You will learn this in future in second year in formation of complexes. Okay, but here in the first year class, you just concern with what outermost shell orbitals, because it is a basic starting point of hybridization and structure of covalent molecules. So when s orbital, which is spherical, an s orbital which is spherical combines with a p orbital of dumbbell. Okay, dumbbell means you all know that it is a laying 8. So when these two orbitals combine, then s never be spherical and p never be dumbbell. They come to the one what intermediate shape. The s orbital starts making a small lobe, and p orbital loses its one of the lobe, and thus these two identified shape and energy wise, they form a new orbital which set are arranged in a special shape. Okay, note this: the central atoms of the covalent molecule undergoes hybridization. So based on the hybridization of central atom, we can predict the shape. So if in a molecule the central atom undergoes sp hybridization, the shape must be linear with a bond angle of 180 degrees. Or if the central atom undergoes sp2 hybridization, means one s orbital, two p orbitals. Two p orbitals, the shape must be triangular planar with the bond angle of 120 degrees. So in the same way, methane, water, CCl4, ammonia, so and so, etc. molecules, all oxyacids of sulfur, all oxyacids of chlorine, which undergoes where central atom undergoes sp3, means one s orbital combines with three p orbitals. So one s, three p, 1 plus 3, 4 orbitals are formed. And these 4 orbitals arrange in tetrahedral shape. Tetrahedral shape with an angle of 109 degrees 28 minutes. So see here in ammonia, in ammonia, in the same way, what I explained now, in the same way in ammonia and nitrogen, the central atoms are here. Nitrogen is a central atom in ammonia, and there oxygen is a central atom in water. So this nitrogen of ammonia is undergoing sp3 hybridization. It is sp3. It is sp3 hybridized. So when it is sp3, the shape must be tetrahedral with 109 degrees 28 minutes. But here the shape of this ammonia is no more tetrahedral, no more the bond angle is 109 degrees 28 minutes, which is proven experimentally. It is found that the shape is pyramidal. Okay, the shape is pyramidal. Okay, the shape is pyramidal, and the angle is about between the H and H. The bond angle is found to be 107 degrees. Okay, why? See here how it is sp3. Ammonia, in ammonia, the nitrogen central atom, its atomic number is 7. Okay, that is 1s2, 2s2, 2p3. Now this 2p3, this 2p3 I can write as 2px, 2py, 2pz. Now atomic number 7. So here see 1, 1, 2, 3. So here in nitrogen there is a first shell and a second shell. The second shell is the outermost shell, in which it is having the 2s, 2px, 2py, 2pz. 4 different orbitals. Here So 4 orbitals are there and 5 electrons. So these orbitals, one s orbital and 1, 2, 3, 3 p orbitals. Okay, 3 p orbitals, one s orbital, 3 p orbitals combined form 4 identical orbitals sp3, sp3, sp3. So the shape of these orbitals is what? Here their S never be spherical after intermixing, hybridized, or P never be dumbbell. They acquire a different shape. What is that? This spherical starts making a lobe. Okay, and this p orbital starts losing a lobe. So all the 4 orbitals of sp3 will be identical. So we find 4 such type of partially lobed orbitals are produced. So these orbitals of nitrogen arranged in this line. Okay, first orbital, second orbital, third orbital, and this is fourth orbital. Now, how many electrons in the central is what here? This is around the nitrogen. Okay, nitrogen valence shell. So around this, see how many valence electrons? 2 plus 1 plus 1 plus 1, total 5. 1. See, according to hybrid, okay, you have to fill electron, whether it is pure atomic orbitals or hybrid orbitals, all or even molecular orbital theory. According to molecular orbital theory also, wherever you fill electrons, you have to fill the electrons according to above principle, Hund's rule and Pauli's exclusion principle. So here we have 5 electrons. So since here all the electrons are identical, same energy. So first fill each orbital with a single, which is according to Hund's rule. The next pairing according to Pauli's. Okay, means in an orbital, the 2 electrons must spin in opposite direction. And note at the same time, when the bond is formed by overlapping of orbitals, the 2 electrons of 2 different orbitals which are overlapping, they must spin pair after bond formation. Okay, so this is what central nitrogen. Nitrogen. Now, here this nitrogen is combining with what? 3 hydrogens. And we all know that the hydrogen provides its 1s electron. So here the 1s electron is present in spherical s orbital. S orbital. So these are 3 hydrogens. Now these 3 hydrogens are providing its 1s electron, okay, which is in a spherical orbital. So it is overlapping the s orbital overlapping with the sp3. So first NH bond, next it is second NH bond, third NH bond is formed. So around this 1, 2, 3, 3 bonds are formed, and there is a pair of electrons left. So here here on the central atom of nitrogen, what we see here on the nitrogen, there is, okay, though it is sp3 hybridized, okay, though it is sp3 hybridized, here one of the hybrid orbital, this is green color I'm shading. This orbital is having the pair of electrons which are not participated, okay, which are not participated in the bond formation. And such pair is called as a lone pair. It's called as a lone pair of electrons. Okay, it is called as lone pair of electrons. Okay, so here this lone pairs. See, this is what the lone pair of electrons which are not participated in a bond formation. But remember, the lone pair also will be present in hybrid orbitals. And the remaining 3 NH bonds. These are what? Bond pair of electrons. Bond pair of electrons. How many we have here in ammonia? 1, 2, 3. 1, 2, 3. So 3 bond pairs. And these also will be present in hybrid orbitals. So it's a shortcut that if we know the atomic number of an element of a molecule, and that is especially the central atom of a molecule, means few atoms, elements, we should know atomic number, their valence shell configuration, and a basic concept that the lone pair of electrons and the bond pair of electrons always related to the related or present in the number of hybrid orbitals. So this lone pairs and bond pairs always present in hybrid orbitals. So here around nitrogen, one lone pair, three bond pairs. So here four hybrid orbitals, that is sp3, sp3. Okay, it's a shortcut to identify the hybridization of any molecule. So here the shape must be what? Tetrahedral. But here the shape is pyramidal. Why? So according to, so practically it is pyramidal and the bond angle is 107 degrees. To explain that only we are learning here VSEPR theory. And this theory gives you the exact shape. So according to three highlights, this theory, three highlights are there. We have to consider, the first, how many pair of electrons in the valence shell of central atom of a covalent molecule. Okay, so here in the valence shell, okay, in the valence shell of central atom, what you have? A lone pair of electrons and bond pair of electrons. Okay, lone pair of electrons and bond pair of electrons. And if you see the structure, the bond pair is in between two nucleus. Okay, here NH bond is there. This NH bond pair is related to two nuclei, nitrogen nucleus and hydrogen nucleus. Means the movement, always we know that electron, whether it is electron single or electron pair, they will be what? Spinning around its axis, or the bonds will be vibrating. So the movement of this bond pairs is controlled by two nuclei. Okay, two nuclei. So the vibrations or rotations of bond pairs are lesser compared to lone pairs, because the lone pair is related to only one atom. See here, this lone pair is related to only nitrogen, but here bond pair related to both nitrogen and hydrogen. So whether it is bond pair or lone pair, the electrons always spins, they vibrate, they rotate. So the vibrations, rotations, disturbance, we can say simply disturbance is caused by lone pair is more compared to bond pairs. So one has to first consider the lone pairs and bond pairs of the central atom. The sum of this is hybridization. It's a shortcut. Okay. And remember, the lone pair and bond pair always they repel. Okay. Because any pair, it is electron. And electron is negative charge. So here in the bond pair, two electrons are there. Both electrons are negative charge. Okay. And at the same time, two pair of electrons are together, whether it is bond pair or lone pair or bond pair. Always electrons, because of same charges, they repel with each other. And since they have same charges, the repulsions will be more. So a molecule which contain the bond pairs along with lone pairs will have three types of repulsions. One is repulsion between the lone pair. Okay. The next is lone pair, bond pair. And next is bond pair, bond pair. Okay. So as we know that the lone pair belongs to single atom, the disturbance or repulsions caused by the lone pair is more. So lone pair repulsions are more, and lone pair bond pair repulsions are lesser compared to lone pair, and more than the bond pair. Okay, so this is what the order of repulsions. So as we predict the shape of molecules according to VSEPR theory. Okay, so you just consider the arrangement of bond pairs. Okay, consider the bond pairs, and we need not to consider the lone pairs. Means here three bond pairs are there, one lone pair. So you need not to consider the presence of this lone pair. So along with this lone pair, the shape is what? Tetrahedron. Okay, if you consider this one, okay, I have taken the model. Now this green is what? This green is what? Lone pair. The white is hydrogens. The black is nitrogen. So here see, if you consider the lone pair, the shape is what? Tetrahedral. Tetrahedral. Okay, but if you avoid this lone pair, the shape is nowadays tetra. What is this one? Pyramidal. It is a pyramidal. Okay, so according to VSEPR theory, avoid the lone pair and try to predict or say the shape of molecule based on arrangement of a bond pair of electrons. This is one thing. And next, so here the shape of ammonia is a pyramidal. And next, one more thing, when you consider the only bond pairs, so here sometimes you may get, okay, now need not to consider the bond pairs, some lone pairs I told. Sometimes here in a molecule you may get a single bond, okay, like NH is single bond. Sometimes you get a single bond, okay, and sometimes you may get a double bond also, like SO2, sulfur dioxide. In sulfur dioxide, around the sulfur you find two oxygens, and each oxygen with a double bond with a sulfur, like this. It is SO2. Okay, now here double bond is there and lone pair will be present on the sulfur. So this, in double bond, two bonds are there. And we all know that in a double bond, the one is sigma, next is a pi. So remember, when you give the shape according to VSEPR theory, consider this double bond also as a single bond, because the pi bond is along the direction of sigma. Okay, and at the same time, triple bond. If you find a triple bond, like in acetylene alkynes, we find carbon-carbon triple bond. So where in triple bond, one sigma bond, two pi bonds are there. Okay, one sigma bond, two pi bonds are there. But all these bonds of triple bond will be in same direction as a sigma bond. So remember, whether it is a double bond or triple bond around the central atom, it is considered as a single bond. This you have to remember. Okay, so this is one more point. And next, last point, see here, always due to repulsions between the lone pair or lone pair or bond pair, due to repulsions, what happens, some change is brought, okay, some change is observed in bond angle. So here see, in this molecule, because of here only one lone pair is there. So this ammonia molecule doesn't have any lone pair repulsion. If two lone pairs are there, means on the central atom more than one lone pair is there, then the two lone pairs will repel. But here on the central atom of ammonia, that is on nitrogen, only lone pairs. One lone pair is there and three bond pairs. So this molecule is having what? Repulsion between the lone pair and bond pairs, and repulsion between the bond pairs. So this is having what? Lone pair, lone bond pair, and bond pair repulsions. So remember, it is what? Nature. Okay, it's a nature. We are studying science. So nature has its what? Assessment to get how to get stable. Okay, so the nature arranges in a such a way that in a least energetic and most stable form. So automatically, spontaneously, on its own, this lone pair try to be in safest direction. So to avoid the repulsions itself with the bond pairs, the lone pairs of this nitrogen ammonia will be pulled upwards. Okay, if it is so like this, as I showed in the kit, the shape must be tetrahedral. But automatically what happens, the lone pair itself, like someone is ordered, but here no one is telling the molecule to arrange the lone pairs in such a way. So automatically, spontaneously, that is naturally, the lone pair arranged in a such way that means it is getting isolated. It moves upwards. Okay, the lone pair is moving upwards. Okay, is moving upwards to avoid the repulsions. Like no one wants fights, okay, among them. So like that, the lone pair arranges in a such a way that it will be what little pulled upwards, itself pulled upwards, or it will be moving upwards. So as it's moving upwards, what happens? The bond pairs will come closer. So when this happens, because of this, when bond lone pair is pulled upwards and due to repulsion, then these bond pairs will come closer. So just see here, when I hold this three bonds, okay, three bond pairs in my hand, and if I pull this lone pair upwards, what you see that some a pyramidal shape, okay, like Egypt pyramidal, you see this, okay, pyramidal shape is observed, and now you avoid this, okay, avoid this lone pair. Now shape is what it is, pyramidal. So why ammonia? Why ammonia is pyramidal shape and the bond angle is not 109 degrees but not 7 degrees. So due to lone pair bond pair repulsions, the bond angle decreased to 107 degrees. 107 degrees. And the shape is only according to bond pairs, not by the all the pair of electrons present in the valence shell. So the shape is pyramidal. The bond angle is 107 degrees. Note, sometimes the bond angle may increase and decrease also. Okay. For this, in future, you will learn F2O molecule, okay, F2O molecule, sorry, OF2 molecule and Cl2O molecule. Okay, where one will have 103, other will have 111 degrees respectively based on their electronegativities. For IP, this is not required. And next, okay, next I'll take one more example. See here, we have written here water molecule. So, what is the central atom in the water molecule? What is a central atom in the water molecule? Central atom means obviously in a molecule there will be certain number of atoms. The total number of atoms in a molecule is called atomicity. So here see, in a water molecule, how many atoms are there? Two hydrogens and one oxygen. So it's a polyatomic, triatomic molecule. And any molecule, okay, which contain single atom, okay, any molecule in which one single element is there, means in this triatomic molecule, the oxygen atom is a single. The single atom is a central atom. Sometimes in a polymeric structure or a big molecule, more than one central atom will be there. Okay, that is different. Here in this triatomic molecule, the oxygen is central atom. Like in tetratomic molecule, NH3, one nitrogen, three hydrogens, nitrogen is a central atom. So in a water molecule, the oxygen is a central atom, and we all know that the oxygen atomic number is 8. Oxygen atomic number is 8. Okay, that is configuration 1s2, 2s2, and this is 2px2, 2py1, 2pz1. And we all know that, like in ammonia, this 2s2, 2px2, 2py1, 2pz1, these orbitals undergo hybridization, and like in nitrogen, like in nitrogen of ammonia, same the oxygens of the oxygens of the oxygens of water molecule undergoing the hybridization to form sp3 orbitals. So see here, one s orbital, 1, 2, 3, 3p orbitals combine, 3p orbitals combine to form 4 sp3 orbitals. Okay, in case of ammonia, in nitrogen, 5 valence electrons were there, but in case of oxygen, there is 6 electrons, 2s2, 2px2, 2py1, 2pz1, 6 electrons. So same once again, when you fill the electrons in hybrid orbitals, must follow the Hund's rule and Pauli's principle. So first fill each hybrid orbital with one electron each and with the same spin. After that, pairing with the opposite spin. Okay. So now here on filling these orbitals, 4 orbitals with 6 electrons, you got 2 sp3 orbitals with a pair of electrons and other 2 sp3 orbitals with 1 electron each. So here the one electron containing orbitals, this one electron containing orbital, they overlap with the 1s orbital of hydrogen, 1s orbital of hydrogen and form OH bond. And when the sp3 orbital of oxygen overlapping with s orbital, pairing of electron takes place. So this is what OH bond formed by overlapping of sp3 orbital, sp3 orbital of oxygen and s orbital of hydrogen, s orbital of hydrogen. Okay, and next here this one also same, other bond also here sp3 orbital of oxygen and s orbital of hydrogen and form OH bond, second OH bond. So on the oxygen, you can see here, you can see that in H2O molecule, in water molecule, you can see that there is a 4 electron pairs. There is a 4 electron pairs where you can see these are 2 bond pairs. First OH bond, second OH bond. BP means bond pairs. And the remaining 2 sp3 orbitals have a lone pair of electrons which are not participating, in any bond formation. I'm shading with the red marker. Here it is. Okay. So these are what lone pair of electrons. So on the central atom of water molecule, that is oxygen, there is 2 lone pairs and 2 bond pairs. And as I just now told, the lone pairs and bond pairs always be in hybrid orbitals. So the sum of the lone pairs and bond pairs is a hybridization of central atom. It's a shortcut method to predict the shape, geometry or bond angle of molecules, covalent molecules according to VSEPR theory. So it is what? 4 hybrid orbitals. So it is sp3. So though it is sp3, the shape is not tetrahedral. Why? Because as it is having the lone pair, okay, lone pair, 2 lone pairs. This is having what? Lone pair repulsions. And it is having what? Bond pairs also. This molecule is having lone pair, bond pair repulsions also. And there is a bond pair repulsions are also. So as we know the order of repulsions, the lone pair repulsions are more than the lone pair bond pair and even more than the bond pair. So due to this high repulsions between the 2 lone pairs, the bond angle much more decreases. So simply remember, as number of lone pairs on the central atom increases, the bond angle much decreases, or say sometimes much increase also. We may get some molecules in the future. Okay, so here it will change. It will change because you have one molecule where bond angle is 111 degrees. 111 degrees. Okay, so here now the bond angle is no more 109 degrees 28 minutes. It is found to be what? 104 degrees 5 minutes. Why? Because due to this lone pair repulsions, the bond angle decreased to 104 degrees. In the case of ammonia, 107. So one lone pair decreased by 9 minus 7, 2 degrees. Whereas in case of water molecule, 2 lone pairs. So lone pair increased 109, then 104. How much? About 5 degrees. So simply as number of lone pairs increases, repulsions increases, bond angle changes more. Okay, bond angle changes more. And next, as we have to give this shape according to bond pairs. So just see the arrangement of bond pairs. Avoid this lone pairs. Okay. So what is the shape? It is angular shape. It is angular shape. So see this is okay. Now the green are 2 lone pairs. The black is central atom oxygen and the white is hydrogen. So if you see, okay. Now what is this molecule? It is tetrahedral in shape. It is tetrahedral in shape. Now, you can view this molecule in different dimensions as it is a 3D molecule. So, here see, I'm just pointing towards you, the bond pairs. OH bond, OH bond. And these two are what? Green are lone pairs. Okay. So, if you avoid this green, Okay, if you don't say this, green. What is that? The shape is inverted V, angular. So according to VSEPR theory, we have to consider the arrangement of bond weights. Therefore, the shape is angular and inverted V shape. Okay, or you can say V shape also. Nobody will scold you. Okay, and the bond angle is no more 109 degrees. It is 104 degrees because as number of lone pairs increase, repulsions increases, the bond angle decreases. Okay, I hope you understand this. So this may come as a long answer, 8 marks, or sometimes it may be asked for 2 marks or 4 marks. Okay, keep it up.